24. Okay. Now if we add these row sums, what do we get? 45. So this is basically nothing but the sum of all the numbers. Now instead of following this pattern of calculation, if we do something different with the same matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have not named this example, interchanging sums. That's what this example is called. Now instead of considering the rows, if I consider the columns and add the numbers in the columns, in the first column, I get 12. If I add these, I get 15, I get 18. Now if I add these column sums, what do I get? Again 45, of course I will get 45. And this is in fact one technique of seeing whether the total sum of all the numbers in a square array like this is correct or not. So before computers were developed, this is the way some people used to check their calculations. Some huge numbers or many numbers of numbers are to be added, then they would check the calculation in these two ways. If they matched, that means they have got the correct answer. So it seems like in whatever way we add the entries of a matrix, it does not matter. Say if we have an m by n matrix, for example, I can denote this matrix like this: A11, A12, A13, A21, A22, A23. These are the numbers, okay? And these suffixes 1, 1, 1, 2, these are not 11, 12, 13, okay? This is 1, 1 means it appears in the first row for this one and in the first column. 1, 2 means this entry appears in the first row and second column, and so on. So this one appears in the second row and first column. That's why 2, 1. Like that, A31, A33, A34. How can we write the row sums using summation notation? If it's the first row sum, then it will be A1J. You see, 1 is constant here, 1, 1, 1, 2, 1, 3, but the second number is changing. Changing from where to where? From 1 to 3. So this is the first row sum. Similarly, in the second row sum, here there will be 2. In the third row sum, here there will be 3. In general, in the ith row sum, here there will be I. And if we take the sum of all the row sums, then it will go from 1 to 3. This one is equal to, now instead of row, if we are adding along the columns, for the first column, see, along the column, the second number stays the same, the first number changes. So Aij, the first number is changing, I is varying from 1 to 3, and then we are adding these column sums. J is varying from 1 to 3. So you see that these two summations have been interchanged. I goes here, J comes out. In this case, in this finite case, it's possible to interchange sums. But what happens if these sums are infinite? Let us now consider an infinite matrix. If you consider this matrix, say, it's an infinite matrix, okay? Here every row, there are infinitely many rows and each row has infinitely many entries. For example, in the first row there is the first entry is 1 and after that all the entries are 0. In the second row the first entry is -1, then the next one is +1, the second one, then from the third one onwards all are 0. So it's following a pattern and then this is shifted. Okay, one place on the right side. Now for this particular matrix, what are the row sums? You see, for the first one, although there are infinitely many numbers, since only finitely many non-zero numbers are there, so we will have a sum. In adding infinitely many zeros gives us 0. So this sum will be 1. However, for the second row, you see that the 0 part is of course 0, but this 1 and -1 cancel. They cancel each other and we are left with 0. And the same is the case with all the other rows. We continue to get 0 row sums. Only one row sum is non-zero, that of the first one, which is 1. So if we add all the row sums, the value is 1. However, if we now concentrate on the columns you see that the sums are all 0. So if we add all the column sums, the value is 0. They are not equal. So unlike the finite case, in the infinite case things can go wrong. Okay, it's not always this. Aij, I varying from 1 to infinity, j varying from 1 to infinity, and the other one, this is the sum of all the row sums, and this is the sum of all the column sums, or I may have said the other thing, it does not matter. What matters is that these two sums are not necessarily the same. Okay, so unlike finite sums, an iterated series, a series of a series, in that you may not be able to change the sums. But it is a very useful thing to be able to do. In some cases, you will find it very useful that we can interchange the sums. In what condition can we do this? For this situation, of course, we cannot do this. So, what is it that we need? So, we will see that. So, do you see how things are going wrong? Simply because we don't know what we are doing. So we are going on creating nonsensical things. So after that, we have, yes, example 1 to 6. This one is interchanging integrals Sometimes we work with functions of more than one independent variable, which, for example, may look like this. This is a function of two independent variables. And if we draw the graph of this, it may look like a surface in 3 dimensions. Something like this. Say this is the x-axis, this is the y-axis, and this is the z-axis. The surface may look something like this. Just saying, okay, it may be curved. Somewhat like a parallelepiped or a cube. Now, what we want this volume. Since this is not a cube or a parallelepiped, we cannot just simply multiply the length, breadth and height. We cannot do that because there may be some depression, something else. The surface is irregular and it entirely depends on this function. So in this case, if you recall from calculus, using integration we can find its volume. So what we can do, we can slice the volume with some slices along the x-axis. That is, we can consider sections like this, cross sections. Okay? We can consider cross sections like this which are parallel to y-axis. And if we find this integral, that will give me the area of the cross section under this curve. Okay, this surface, where the surface meets this vertical plane, there will be a curve of intersection. The area under that curve is given by this ordinary integration. Okay, note that I am not considering the limits. There will be some limits of integration. But anyway, and that area depends on y. It's a function of y because as you move this slice along y-axis, this curve will likely change. So the area will depend on that. Now if you continue doing integration along y-axis of this, that is, if you do this, then that will give you the volume under this surface between so and so limits. If instead of this you decide to consider cross sections along y-axis perpendicular to x-axis, then you will calculate these areas which will depend on the value of x where the cross section is made, and if they are also integrated with respect to x, that will give you the volume. Now from the physicality of the situation, it seems like the volume, in whatever way you calculate the volume, it should have the same value, right? So which means that it does not matter in which way we integrate a function of two variables, first with respect to x, then with respect to y, or first with respect to y, then with respect to x, we should get the same answer. Unfortunately, by now you have already seen many things failing. This is also not the case always. And one such example is this. Let us calculate this integral e to the power minus xy e to the power minus xy dx dy. Okay, let's calculate this integral, and then we will see that if we change the order of integration, we will get a different answer. Now for this, the inner integral has to be calculated first. So we do that. 0 to infinity e to the power minus xy e to the power minus xy with respect to x. Now when we are integrating with respect to x, y is considered to be constant. Okay, y does not take any particular value, but y is arbitrarily constant. It's arbitrary but considered to be constant.